Welcome to Build with Naz. Hi, I'm Naz. I'm the CEO and founder of Rebel and the author of Developer Life and maintainer of the Rebel 2e crates. I believe that open source comes from an open heart and from the joy of coding. In today's video, I want to cover something called the newtype design pattern or idiom. It's not as extensive as the type state design pattern or the builder pattern, but it's actually a very important way of describing let's say, because Rust isn't object-oriented, it's a way to essentially create functions that can receive arguments expressed in a kind of a vague way. So I guess the word I was trying to avoid using is polymorphic behavior, but essentially you want to write a function, but let's say it takes a type. In Rust, it'll be a concrete type. With generics, you can sort of monomorphize the output of functions, like one for each concrete type based on the generic constraints. But let's say that you don't want to. Let's say you want to use generics, but also you want to make it so that there's a lot of flexibility in converting whatever you give to this function as an argument into another concrete type. And so that's this into Impl pattern. So we're going to be looking at into Impl of a concrete type, and one of the things that feeds into that is this new type pattern. And the new type pattern just is a way to wrap an existing type with a different type, and then from the compiler's perspective, that ends up becoming a new type. And this is a great way to get around using really sort of generic types like usize or string or a string slice. Because like, for example, I recently went through a 3-month refactoring of the Rebel 2e code base, and I was using usizes everywhere for representing positional arguments, which is like that row and column index on a screen, and also the width and the height. So already there's, and those are all usizes. Actually, it's not exactly usizes. I was also using crossterm, which used u16. So this led to a lot of sort of having to wrestle between converting these sort of low-level primitive types, so to speak, or scalar types. And so by using new type, I was able to disambiguate length units from index units, and that also had the added benefit of avoiding off by one errors. Because if you think about an index might go it starts at 0. So 0 is like, let's say, the first item in an array, but let's say the length of the array is 5, so the maximum index is 4, and so there's a disparity there. But then the length of the array when it's empty is 0. So to handle, of course, all of this can be represented by either signed or unsigned integers. In Rust, if you use unsigned integers and you subtract, then you can get into this underflow, or essentially like trying to, let's say you have a usize and you're trying to put a negative number in it. That's not going to work because it's unsigned. So to get rid of all these sort of corner cases where you might have like a off by one error, or there's a situation where numbers can't be negative or whatever it is, instead of thinking really hard about it and trying to handle it by writing a lot of tests, what I want to show you in today's video, this live coding video, is how could we just simply eliminate that entire class of problems, so won't even bother us. So the way we're going to do that is, I'm actually going to use a real example that I ended up implementing for the Rebel 2e crates, but I'll do a much simpler version where one of the most basic things in the 2e is that you have to represent the position on the terminal screen, let's say, which can be a row and a column index, and you also have to specify the bounds, and the bounds is like, you can think of it as a bounding box, like in CSS. So you have like a width and a height. So essentially, when you specify a point, which is a x and a y, or a row and a column index, and a width and a height, you get a box which has an origin. So And so that's one of the most fundamental things in doing a box layout for the TUI. And when I went and rewrote almost, I think it was like 33% or 50% of the code has been rewritten. Basically, it was a massive refactor for 3 months because I had to pay down a lot of technical debt. But this new type pattern thing was something I leaned into heavily, and it just eliminated an entire class of problems for even emerging. And I didn't have to be too careful about using this code. Like initially, the code that I was rewriting was very complex, and by introducing this pattern, the complexity collapsed on itself, and it was just like condensed and removed by the simplicity of this pattern, which is amazing. So this entire video, we're just going to be creating something called a size and a point, and we'll do it in a very sort of simplistic manner, and then layer on this new type pattern and use into Impl, and then see the benefits of doing that. So with that, let's get started. Another thing I wanted to show is, and I'll put a link to this in the description of the video, but there's pretty good information about this new type idiom in Rust by example, and there's a pretty good video of compiler-driven development in this talk, and Jacob does a really good job explaining, like, you know, what this new type pattern is, when it's used, and how it really makes you like use the compiler, lean on it pretty heavily as part of the development process itself and the design process. So that's pretty awesome. So with that, the project we're going to be making is, let me create a new, I think I'll just call this new type pattern. And let us open this in new type pattern. Okay, and here we go. All right. So to get started, what we are going to do is, so let's see. So we're going to create a bunch of like the simplest sort of, without thinking too hard about it, like what would this, how would we solve this problem? And the problem is, you know, representing essentially a point and a width and a height in a very naive way. So let's call that example 1. So we can do that mod example 1. And then later on we'll add more examples to clean it up and make it better. So here, let's see. So we have mod example 1. And so the first thing we're going to do here is, let's see. So the, let's see. So I guess the simplest thing to think about is we have two structs, like just because we're doing a layout and a size and positioning and size basically. And so for that we just have, we can just call this, let's say, pub struct. Actually, there didn't need to be pub. I don't think we're going to be using this again. So we're just going to call it like point. And we can do x is usize and y is usize. So, and actually let's do a couple of derives. And let's do partial EQ because we're going to be doing, in tests, we need the partial EQ. Okay, so that's pretty much it. That's a x and a y, nothing too interesting, but I will go through and cause a lot of problems using this simplistic approach. So here we have, this to illustrate why, even though this seems simple, there's actually quite a bit of complexity that comes out of this. So this isn't really as simple as possible. So let's say that we have a bunch of tests that we write with this, and what we can do is, so at the most sort of the naive, the naivest approach is this. We just do fn test simple. So here we just make like, we create an x, we create a y, and then we can create a point. So that's x and y. That's pretty straightforward. So we have a width and a height, and we can create a size. So it's like, wow, that's really, I mean, that's it. it's pretty straightforward. It's nothing really to think about there. But because everything is usize and everything is pub, like there's I'm gonna start breaking this apart by showing how positional arguments fall apart, how we can take a width and assign it to an x or a y, we can take a y and assign it to a width or a height. I mean, just pretty much go sort of crazy, and then see how all of this like spectacularly falls apart, even though it seems quote unquote simple. So this is pretty straightforward. So let's kind of tee it up by adding some constructors. And so here, notice that each of the fields are the same type, usize. So you can't really, from a compiler perspective, you can't really tell one apart from the other. Like they're all usize. I have 4 usizes and basically distributed across 2 structs. And then if I want, and I see this, and this is, I'm not picking on crossterm, but in crossterm, for example, a lot of the APIs take a tuple, and the tuple has 2 U16s. The first one is, I think, see, I can't even remember. It's either row or column. I don't know. But one is row, the other one is column, and it's positional, and they're both U16. So and it's a tuple, so you can just very easily mix up the row and the column. So we want to avoid situations like that. But I'm going to induce that sort of pattern by creating some fancy constructors. So let's do some fancy constructors here. We can say implement, just like in crossterm, you take 2 usizes, and note that the first usize, because positionally, these are positional, we implicitly encode this to be the x value, and we implicitly encode that to be the y value, and it's implicit. It doesn't say anywhere. And I can easily pass even though I intended this to be x and that to be y, I can pass y first and x second. There's literally nothing stopping me from doing this, which is the problem. And so I can do it the other way around. So for point, like that's a fancy constructor. We can do a similar fancy constructor for size, where again it's positional. The first one is width, and the second one is height. Okay. So with that kind of teed up, let's see if our tests run and does everything build. Yep. Okay. Looks good. Okay. So now what we're going to do is start breaking stuff. So let's do an off by 1 error. So let's say that say off by 1, and we're actually anticipating that this is going to fail. So we're going to say should panic. All right. So this is I'm going to make a size, and I'm going to, let's say, make it 100 by 200. And then what I'm going to do is I'm going to make a point, and this point is supposed to represent the bottom left coordinate of a box, assuming this origin is 0, 0. So here we can say the end point would be, let's say, actually that's what it should be, but I'm going to, Copilot did the right thing, but I'm going to induce it to do the wrong thing. So this should be, oops, point x, let me see. Okay, so this should be, well, I mean, actually, Copilot had the correct answer. It should be like 99, and y should be 199. But it obviously that's not what I'm doing here, because I want to induce this error. So so here we can say assert equal the end points x plus 1 should be the size width, and obviously this is not going to work. I mean, the test passes because we expected it to fail. Like if I take this away, see, it fails. Okay, because we know that we set it up. This one is a pretty heavy setup, but this kind of stuff happens all the time, especially when you're positioning things where there's like I have a layout manager which computes the size of boxes and then decides how much screen space to give each one, and then paints, and it has to do things like clipping and scrolling, and all of this becomes very relevant, in practice. Okay, so this is the, quote unquote off by one. So by the end of this video, we're gonna, using this new type design pattern, we're gonna eliminate this from happening in the first place. This is gonna be something that simply doesn't happen. Okay, so now another issue that I have with this current quote unquote simple design is the positional arguments. Positional arguments that are not decorated by distinctive types are just easy to get wrong. It just, so we can do positional argument constructor problems, right? So here we have, so we're going to do something, because we have these fancy constructors which take a tuple, and I have no idea. I mean, just by looking at the tuple and the types, I can't tell you that this is, what is this supposed to be? Is this supposed to be width, height, x, y? No idea. So here we can say, let's make a new point. So we can say point, and now we're going to use that fancy tuple thing. So 10, 20 into, and so what this does is that it converts, this is the, I mean, we know this because we just wrote this, but this is the x and that's the y. So here, which is terrible. Like if you're having to write comments like this, that's another kind of hint that perhaps new type pattern should be used, because this is easy to get wrong. I mean, this is so easy to get wrong. So we can do size 1, which is size, and we can say with this, let's say 50 and 100, whatever. Okay, so now we have a point in a set, and I'm going to go ahead and mix everything up and say mix up the x and y values, and fail. So we can make a new point, and we can say here, I'm going to take the y value from point 1 and pass it as the first argument in the tuple. And then the second is supposed to be a y, but I'm passing an x. I'm intentionally flipping it, and this assertion will fail. Point 1 should, let's just say I intended it to be the same. And this is a typo, like, easy to make this mistake. So when I run it, again, the test is passing because I anticipate, this is backwards. I anticipated the test to fail, so it is failing as expected. Okay, so that is definitely something that we can mix up like pretty easily. Similarly, the width and the height can be messed up. So let's say that actually I can, so if you think about it, I can say let size 2 equals, I'm expecting the width and the height, and again, this is assert equals, it's supposed to be the height, I passed the width. What's the problem here? Oh, we don't have the this one. Basically, I forgot to put this derive partially q. Otherwise, there's the equality is not implemented. Okay, so this will also fail. So let's say if I comment this out, this should fail. I mean, actually, these should be separate tests, but I'm just being a little bit lazy here. Okay, finally, I'm going to mix up all the values. The x's and the y's and the width and the height, and we have no idea what's going on anymore. So we say let point 3, it's going to be, I'm going to grab the size, I'm going to grab its width, and I'm going to put actually, why not? Let's grab its height, because again, I can do whatever. I can grab this one like 0.2, and I'm putting its x value in here. And obviously, this is nonsense. Like, this is not going to be 0.1. So even if we comment these out, this test will still fail. So there you go. So how to fix this? This was like, like just go. Okay, this is the very naive approach. Let's save this. So we just got the sort of the very naive implementation done. We haven't seen any new type, but how do we start sort of new typing this? And that's what we're going to do next. Okay, let's jump right into the new type pattern. So let's see. We're going to put that in example 2 actually. So let's see. I think we had example 1 done. Okay, so I think I'm going to follow these notes. So example 2. So the first thing, that's great. We did the pitfalls and we used usize everywhere. And now we're going to introduce new type. So here we're going to essentially, let's see, mod example 2. We're going to we're going to take this, we're going to take the point and the size and we're going to deconstruct it into smaller composable types. And those smaller composable types will be distinct types, but they will essentially be wrappers on top of usize. So to kind of generalize it even further, I'm going to use something called type alias. And I'm going to define my own number type. And instead of using usize, just for the purposes of this sort of video, I'm going to use this thing, u16. So, and then, so let's see. So this is roughly what the new type pattern looks like. So you create a new struct, and that struct simply wraps another type. So that's literally it. So if we wanted this value to be publicly accessible outside of this particular module, we could make this pub, or we can implement a bunch of these. This one, the deref and deref mute actually, deref mute. These traits, and I'll show multiple variants of this. So we can do mod x ups. So here we can. This is just to kind of keep the code co-located. So we can do implement the deref trait for x, where we just get a pointer to essentially a reference to the borrowed value inside of x. So that essentially gives us this value, but we can't modify it. If we wanted to modify it, we can implement something called deref mute, and let's see what that does is it allows us to basically get a mutable reference to whatever's contained inside of x, and then we can use the assignment operator to actually put values in here. So that's essentially the most simple sort of form of this new type pattern. And another benefit is that, so this is kind of like the Rust, the orphan rule. So if you are trying to implement a trait on a struct and you don't have, that trait and the struct are not in your current crate, then the orphan rule says that you can't do it. So let's say I cannot implement debug for usize, but I can implement debug for x. So let's bring that in. So this, we just need debug. So here we can say, and this is just to show that it can be done. So we say implement debug for x, and all we're doing is just saying, okay, it's a fancy printout of x with the value in it. So this is kind of cool. Like this is, we can get around orphan rule oftentimes just by using new type. That's another completely valid use case. So here, this is, if you want, you can even do stuff like this. I mean, depending on like what your use case is. In our example, we're not actually gonna give direct access to the number, and so the deref and the deref mute are plenty. So that takes care of one of them. Actually, let's do this, derive. I'm not gonna derive debug because I've done a, but this is gonna be for tests, basically the partial EQ. Okay, and this is copy. So it's copy and clone because it's just a u16. And so far so good. Like now we haven't really gotten too much farther. We haven't gotten close to where we want to be, but we're getting there. It's actually it's shocking. Like there's a lot of this kind of almost boilerplate-ish code, but once this type of pattern starts getting combined and you start creating composite types, essentially larger types by composing these smaller new types, it gets cool fast and very useful. Okay, so now we need to repeat this for y, and actually before we do that, let's write some tests. Let's do this mod tests, and here we say, okay, so this is, we're gonna do, let's say we're gonna test x, and so we're gonna make an x, we're gonna, so you remember that deref mute? That's what this is. So basically, sorry, not deref mute, deref. This is just deref. Basically, the star x allows us to get to the underlying value, which is a U16, and that's how that comparison works. We can also do .0 because this is still, even though it's not public, this test has access to that private private data, so it's a tuple. Because we did it like this. We could also do it something. We could have done it like this. This is also fine. But then we have to use the struct like with the curly braces. This is totally cool. We could have done it this way. But because there's only one number that's contained in it, I decided might as well just do it the simplest way possible. Okay, so so this obviously won't do anything because x is the, so here, this is actually really good. We can't do this. This is invalid. This is amazing. This is exactly the point of newtype, is that I can no longer compare x to 10, because what is 10? Is 10 an x? Is it a y? Is it a width? Is it a height? I don't know. So, and we'll come back to actually, so what we can do is cool stuff like this. We can say x 10. So now I know, oh, okay, cool. It's that thing, it's that struct, it's that type, it's that new type which wraps which is a wrapper on top of U16. So so then we can also, like, there was a deref mute. We can do something like this. We can say make this mutable, and we can say x actually star x equals 100. So here, when we do this, it should say 100. So if we run this test, ta-da, it works. Yay. So this is us using deref, and this is us using deref mute. So this is one of the Lego building blocks. There's more. So that's so we've done x. So now let's do the same kind of thing. We're gonna say derive all of this, and we're going to say y, and we're going to do mod y ops, just like actually exactly like this. So yep, that's exactly right. So now we can write some tests. This goes pretty fast with Copilot in this case. So we're the same kind of thing, 20 and then 200. Perfect. So now we're going to, surprise, surprise, repeat this for, actually, let's collapse this so it's more readable. So now we're gonna do, let's say, the width and the height. Because the width and the height are really just numbers, just like, they're basically just the same thing, wrappers. It's just that we will give different meanings to these types and how they relate with each other, which is what makes it incredible, because now we can really leverage the compiler for doing our design and our development. So here, same kind of thing. We say struct width and is a number, and we do the same width ops, and then literally the same thing. And here we're going to do the same thing. I can type, okay, test width, yep, same thing, nothing too exciting here. Actually, why don't we just run bacon? Okay, so this will just keep, running the tests for as we build our stuff. Bacon is pretty cool, and next test is also really cool. It's a really nice combo, bacon and next test. Let's see. Okay, so we finished our width. Now we're going to do height, and let's see. the setup for this video is really the time consuming. Once we start implementing this, it'll go pretty quick. So we have the same thing with the height, and now we do a final test, and we say test height, and check it out, it works. So this is constantly running the tests as we're typing, so that's great. Okay. So that's great, that works. And so now that was example 2, where we've taken essentially, this is the new type pattern, and the rest of the video is going to be like how we can leverage this to do really, really, really incredible things that we simply couldn't have done with our OG point and size, which were just essentially containing a bunch of usizes. Okay. So let's see, with that, let's go to the next example. So now that we've handled we've done this, we've done the X, Y, width and height. Let's do this. We're going to use the new type pattern on the point and the size, because we haven't really done anything with point and size. We've just taken care of X, Y, width and height. So let us make another example, and this one we're gonna do. Okay, so we're gonna make a point and a size. I'm just gonna highlight this, and actually let's just do this. Maybe this is easier to read. Not really. Okay, so we're gonna do a point and a size, and this point and the size is gonna be it's actually going to use the code that we've built, the building blocks that were built in example 2. So let me import that. So we can do example 2, and then we can say something like pub struct point, only instead of like, let's say pub X and Y. Notice I didn't use positional here. We could easily just have, let's say, we could do this. We can say pub struct point 2. We could have done like this. We could have just dropped the pubs. I mean, and the reason this is okay to do is because, yes, these are positional, but you know what? I can't mess them up because this is a distinct type from that. They are not the same. Even though under the hood, it's just a number. Because we've written it like this, with the new type pattern, it's not that easy to mess up anymore. Actually, it's not possible to mess up anymore because the compiler will say, hey, I am expecting an X as the first argument, and I'm expecting the Y as the second argument. But for readability, I think this is a lot more readable. So we're gonna go with that. And then just preemptively, let's do that. Notice I didn't derive, I just derived the default debug for this because the custom default was for this. We've always been able to, when you make your own struct, you can obviously implement debug for it, but you couldn't for usize, or you can't for no one can for usize, not you or me, nobody. In Rust, it's not possible. So that's why wrapping the u16 or usize or whatever into a new type makes it a way to get around the orphan rule. Okay, so let's do. That pretty much did it. So width and height, there you go, boom. And this one's going to be really, really straightforward, where I am just going to do a test. And so because everything is strongly typed with new types, there's no generalized usizes used anywhere. I don't have to worry about passing the wrong thing in the wrong place anymore because I can't. So I'm going to say let x equals x of 0. So now x is strongly typed. Notice the compiler is telling me, oh, look, I know the type is x. That's fantastic. That's exactly what we want. And then y, it's saying, okay, I know the type is y. Woohoo. Wonderful. And oh, I see. It's saying that I can't construct it. So you know what? We have to make it pub. So we could just do this. We can make it pub, or I could write a constructor function, but I don't want to do that. So I'm just going to make this pub. Okay. So all right. So we have an x and y value, and then I'm going to say I'm going to make a point, and the point of type P is going to be taking an X and a Y. Look at that. And the compiler's like, okay, that's a type X, that's a type Y, that's a type point. I can, let's see, I can mess them up. Doesn't matter, because you know how this is still strongly typed. It knows that Y goes into Y and X goes into X. How cool is that? So right away, this is an added level of safety. I cannot, quote unquote, mess it up. So when I say assert EQ, I can say point.x is X, and I can say point.y is Y. And that should hold true. Let's see. Ta-da! So right away, I've improved on example 1, where we could just put whatever, wherever. No holds barred. Now, many holds barred. The compiler will just prevent us from shooting ourselves in the foot. This foot gun is now removed. So we can do the same thing with size, and so same kind of thing, where oops, this is wrong. Why did it do this? Let's just roll this back. Height is okay, and then size. Actually, let's do this. I don't like the one-liners. Value, whatever, and here we can do W value. I don't know if this is any better. Okay, so we have a size where we're taking the width. Oh, nice. I didn't see that. Oops, got to be careful with AI. Generative AI can generate all kinds of bugs. Okay, well, it's like humans, so whatever. Okay, so WHS, and I think so far so good. So now we can do assert that the width is the width value and the height is the height value. It's strongly typed. I can't do stuff like this. One compile. Actually, let's do this. This is like won't compile, which is basically why this is the whole point. Already we're yielding the benefits. So I cannot do stuff like this. I cannot compare the width to the height. That's not good. Which is correct. I should not be able to. I cannot compare. Let's say actually, let's do another. I'm going to do a separate test for this. This is going to be I'm going to comment this test out because it's just going to be a bunch of errors. So I can't do stuff like this. I cannot say, so let's say I have an X value, Y value, a point, width, a height, and a size. Okay, so given that setup, I cannot do this. I cannot say assert equals, actually, let's try this. So if I have a new point, let's say, I say point to value, then let's say I wanted to put, there is no by mistake, like I can't mistakenly put a width value in there. It won't compile. I cannot mistakenly, let's say, do this. I can't mistakenly put the X in the Y value. That's not going to compile either. Like, how cool is that? Like, oops. And so similarly, I can't put like a size. I can't do the same with size. So I cannot say the width is an X and the height is a Y. I cannot say that, like, let's say this is width value and this is height value. That'll compile, but this won't. So already, like, these are all of the pitfalls that we ran into with positional arguments, with those fancy constructors. We still haven't resolved off by one, but we're getting there. So there you go. That's this is an example of like reaping the benefits of doing this already. Okay, so that was, let me see, I think that was it. That was a very short example. So now we're going to do the next one. So in the next example, I'm going to introduce that into Impl T pattern. Notice we haven't built the point and the size using these fundamental, let's just call them unit types or basic types or base types yet. So that's going to be coming in not this next example, the one after that. So in this one, I want to create constructor functions that make it really easy to work with those 4 base types. So, and that's where we're going to see the into Impl, like the syntax and how actually we can use it. So we are going to build upon these core types, x, y, width, and height. So we're going to say use super, what was it, 2? Yeah. Example 2, yep, that's right. And then we can do here, we're going to make some constructor functions for x, basically. And so the constructor function for x, there's a bunch of different things that we can pass in that will be turned into x. We can do f64, f32, we can do u8, u16, usize, we can even do string slice, why not, right? So these are all different things. So normally if I were to write this out, right, this is what it would look like. So we're going to do something like too many functions. So this is just to kind of illustrate why we need this. And so here we can say something like super, and here we can say pub fn. I'm just going to call these alt. So I'm going to take an argument of x, which is of type usize, and return an x. And then I'll say something like arg x, and then that's going to be as number. So let's see, what is the problem here? Oh, oops. Okay. Okay, so here we have, okay, so I'm now taking an argument whose concrete type is usize. That's great. We can do x, and in Rust, unlike other languages, you can't have more than one, let's say, function signature. So for example, if, like in some languages you can have like the same function name, but they take different arguments and they're considered like that's okay. But in Rust, if I call something x alt, then I can't have another variant of it with a different set of arguments. It's going to say, nope, you can only have one. So this is again why into Impl T, the thing I'm going to show in just a few seconds, is very relevant. So here now I got to call this thing 2. So as you can see, my function names are getting terrible. So let's do alt 3, and this one's going to be usize. I can keep going. I could say x alt 4. Actually, this one, oops, what the heck? This one is going to be string slice and something like that. So you can say unwrap. Okay, so yikes, no thank you. This looks, this is hard to read and it's just not that great. I'm gonna leave that open just, and then I'll show the better one. So instead, we can say, I'm just gonna call it lowercase x because I don't know, just why not? And here we can say implements the into trait, which takes the generic type, the concrete type of x. I mean, it's generic for into, but x is the generic type argument that I'm passing here, and it returns an x. And what this does is it goes let it x equals argx into and it. Essentially, that's what's happening here. Okay, so far it's not that useful. Like I can't really do much with it. So if I were to write a test, and in this test I say mod tests, and I will say, what the heck is this? I don't know what all this is. So I can say let x val 1 equals x off 0. It's like compiler's like, what do you know? Then it's saying that nothing implements, nothing takes a integer and converts it into x as I am asking it to do here. So the compiler is like, you got to help me out. So this is where it gets cool. I can say let x val 2 is, so let's see, 0. So u16, I can say usize, I can say 0 of u32, and of string slice. So these are like 4 different types that it doesn't work. But notice that my intention is that I just want to pass values, and each one of these values is actually a different type. And because I cannot have for every one of these, it's not feasible to write one of those. What I can do is, using this into Impl T, where T is a concrete type, I can now do this. This is really cool. So we can say mod into Impl X. So here I'm going to write all the, actually, did it do it? Yes, it did. There you go. I know that happened really quickly, but so essentially what it's doing here is that I'm telling the compiler, hey, if you see a usize and somebody's asking you to turn it into an X, this is how you do it. If you see a u16, that's how you do it. If you see a u32, that's how you do it. If you see a string slice, that's how you do it. Which is, I mean, roughly what we did here, right? So it's just that now it's nice and clean and formalized. So just going to do a lot of dead codes. This is strange. Actually, you know what? There's so many of these. Who cares? Yeah. So now notice that our test passed, because I mean the 50,000 warnings is actually, you know what? Let's just clean this up. Just allow dead code, and that should silence that. Yep. And and this one. So here, all of these are going to be the assertion. I mean compiled, but I haven't done any assertions. So I can do the assertions. Yeah, sure, they're all going to be equal to each other, which is all going to be 0, basically. So I can say value 1 is equal to value 2, value 1 is equal to value 3, for, what the heck is going on here? 1 is equal to 2, 1 is equal to 3, 1 is equal to 4. Okay, cool. And let's just run bacon, and it works, yay. So, oh, I see. That's just to get rid of these. I don't like these warnings, so let me just allow dead code. Actually, no, this is unused. Okay, that should get rid of that one. And this one, allow dead code. Excellent. Yay, that's nice and clean. I love it. All right, so that was for X. So now we are able to take a multitude of different types, which we can give to this function X, and it will turn it into caps X. You don't have to use the X function. This is kind of like, you can do the same thing thusly. You can say let's scope this, make another scope, and here we can say, oops, we can say let x value 1. Instead of using this constructor function, I can just say x, and I can say 0 usize into. By the way, this is equivalent, so it does the same thing. As you can see, the Copilot is going to town with this. So essentially, there you go. It all works. So this is the same thing. This is using, you can use this if you like. You don't have to. You can just do it this way. Whatever syntax appeals to you. So this is the constructor function for X. Now we're going to do the same thing and provide the. Actually, let's put a bunch of to-dos. So we can say constructor function for Y, and we also need width, and we need constructor function for height. Okay, so here we can do this to do first, and this is going to be pretty straightforward. Same thing, pub fn y, and notice it's just y dot into. It doesn't. This isn't the interesting part. The interesting part is here, where you say mod, and then for every argument of type that implements the into trait, which takes that y as a generic type argument, then essentially you have to provide a from block for it. So there you go. That's what that looks. Oops. That's what that looks like. And then we can just write some tests for it. Actually, let me leave this open. Let me close test X. This is going to be very, very redundant. Thank goodness for Copilot. This is the kind of stuff that I don't want to write, and it's doing for me. Those tests pass. I can give it a quick look over. The same kind of thing. Y is a constructor function, or I can just do it this way. Okay, done. Now I can repeat for width. And by the way, this for both syntax, I mean, there's absolutely no reason to write it this way. We can just do this because, I mean, that's what it means, because it goes arg y. It knows that this is of type y. So type inference is, we're just leaning into type inference because that's one of the incredible benefits of using Rust and the Rust compiler is the type inference. Yes, compilation times are, take some time, but this is one of the benefits we get, so we should lean into it. Okay, so mod into impl width, same kind of thing, and then I think it missed a brace. Okay, cool, and here we can do, oops, I wonder if it can, oh yeah, perfect, it did the thing, great. So there you go, there's a width, and I think we can do the same thing for height. And notice I'm not doing anything too clever, like having it, creating a declarative macro to do all this stuff. It's like, this is pretty straight. I mean, as you can see, Copilot is generating almost all of this. This is pretty easy to read, very easy to maintain. Like, probably won't be changing much once it's written, so it's okay. There you go, cool. I don't know why I ran that test manually, because it's what's already running here. All right, cool. So that is example 4, where we've now used this into Impl T, and this is an extremely powerful pattern. Like you can use it for configuration objects. It's kind of like a pseudo builder pattern. There's a lot of really cool things you can do with it, but the idea is that you have a function which needs to be polymorphic, but you want it to be strongly typed. And so this is a way to tell the compiler, I have a function that takes an argument. As if you can turn that argument into this concrete type, I'm good to go. I can use it. And then you or somebody else will have to provide all of these from implementation blocks in order to facilitate that translation from let's say usize to y, or usize to width or height, or whatever it is. And the benefit is that we end up getting concrete types, and it becomes very easy to create these concrete types out of lower level types like usizes, u16s, u32s, and even string slices. So that was example number 4. So now it's going to get very interesting, and the code is actually very small. So now we're going to finally leverage these base classes or lower level classes, and we're going to combine them into width and height. And we're going to do it in a very different way than what you might have seen. We're going to use the add operator. So yeah, that's the next example. So in the next example, we're just going to take the base types, or the core types that we've created so far, and these core types are all new types that are assembled on top of number, which is u16. We're going to use them to compose the point and the size, which was like what we did here, a point and the size. And so it's kind of a beginning. We're kind of circling to the beginning, and now we're going to see the full benefits of using the newtype pattern. So here we're going to use the, let's see, I think example 2. Yeah, we're going to use example 2 and example 3 because that's where we define these things. So so here we're going to say example 2, example 3, and another one we're going to do is add the add operator. So the syntax that, so I'm going to actually write the syntax first that I want. So we can, in the test, the syntax that I would like to see is something along the lines of test point, and I want to take, so what is a point? A point is an X and a Y. So what I want to do is I want to create an X and a Y, and I want to say p value 1 is quite simply X value plus Y value. Or it could be Y value plus X value, meaning that I don't particularly care about the order. Because they're explicitly typed. This one is of type X and that one is of type Y, so the compiler can disambiguate one from the other, but I would like for this syntax to be implemented. So how do we do that? The way we do that is we say something, let's make this one, say Impl, it's actually Impl, we're going to implement ops for point. So here we can say super, oops, what the heck, and then here we could say, let's see, what is the Impl ops? Okay, so here, so essentially the add trait goes something like this. If you want to add, let's say, so if you look at the syntax, I'm taking an X and I'm adding it to a Y, or I'm taking a Y and adding it to an X. So it goes something like this: X for Y, and the output is a point. And so the way we do this is we say let X value is, let's say self, nope, that's Y value. And let X value is right hand side, yep. And then we're going to say we're getting a point of X value and Y value, roughly, is what's happening. So this one, as you can see, the red went away. Similarly, we can do implement add Y for X, and this red went away. How cool is that? So here we have, let's say, actually, why don't we just do this? Just say p value 1, and we were going to do p value 2. Does that work? Yes, it does. So so essentially what we've done is that we've said that when you add an X, something that's of type X to something that's of type Y, you're going to get back a point, which is really cool. Similarly, we can do, so that was point. So let's say we want to do something similar for size. So this is, let's just delete all this. So we want same kind of thing, where we want the width and the height, or the height and the width, either ways, we want them to be combined, and we want to get a size type. And so how do we implement that? Exactly the same way. So we go mod implement ops size, and here we can say use super that when we add a width to a height, we add a size. And notice like throughout this process, right? I can't mess it up. I cannot do this. Look at that, compiler error. I cannot do that, compiler error. Like I can't put the wrong thing in the wrong place because the compiler, because of these new types that were built on top of those really, really low level scalar types. We took the scalar types, we wrapped them, we made them, you know, new types that are concrete. And then now we're able to express our code using our concrete type systems, which are built on top of those wrappers on top of those scalar types. So this new type pattern is seemingly very simple, but actually yields a lot of really nice outcomes like this. So as you can tell, I'm very excited about it. Like 3 months of refactoring in like, whew, like there's I think like 70,000 lines of code or something like that in the TUI crates, and I mean it was painful. I've been working on it for about 2 years and a few months, 2 months, 3 months, and so much technical debt got accrued that, you know, I had to essentially use the new type pattern and a whole bunch of other things, this into Impl T pattern, to really clean up the stuff, the code, so that it was maintainable even for me. Okay, so as you can see, the compiler red went away and our test pass. How cool is that? So once we have those core types, it becomes very easy to build on top of it. So similarly, I mean, this is with this, you know, if we wanted, we could also make constructor functions. I mean, that's trivial. So if you, like, for example, we could do something like this. Let's say we wanted point arg point like this, and we can do similarly size. Yeah, again, nothing that interesting or insightful. It's just that if we want it, we can now support like a different kind of syntax. We can say p value 3 is so we won't, so this is a bit redundant. It's not like we're taking a tuple or anything. We're just gonna be doing this. So I mean, it doesn't make that much of a difference, because I mean, this pretty much takes care of the magic. Like, this is just if you wanted to make it explicit for readability purposes, you could do it that way, and the assertions would still hold. So, and now we can do something similar here. So, and again, the ordering doesn't matter. Notice it's flipped and it still works. So there you go. Actually, so that takes care of this one. So this was the sort of like one of the key benefits, is that we want to make an API not just easy to use, but we want to make it difficult to use incorrectly. Easy to use and intuitive isn't far enough. Making it really, really, really hard, if you know, at best case, impossible to use the wrong way, is, I think, the safest approach. And this is an expression of that. So with that, we have actually 2 more examples to kind of wrap this up. But yeah, this is like the majority of the value, I think, that we can get. So now we're gonna address the off by 1 problem, which we found in example 1. So in the first example, I introduced a pretty egregious off by 1 error, just explicitly, but what I was trying to demonstrate here is like thinking about converting a length to an index. Like, there's always some, like, that indices start at 0, but length can also be 0. But the meaning of like length 1, and when length is 1, index is 0. Like it's confusing. Makes sense from a memory layout perspective, but just talking it out or even thinking about it, it's not the most intuitive thing. So how can we address that using our fancy knowledge with newtype? And so we're gonna address that in this one. So let's start by taking the core types that we introduced to x, y, width, and height, and we're going to use those to actually build upon here. And so So essentially, I'm just going to write out what I'm intending to say. So when we go from a width and we want to convert that to like, let's say x, so because width is horizontal, so we go from argument width, which can be like into impl. Actually, no, it can't. Actually, it has to be width, unless we actually, can we do this? Impl into width. Probably not. Yeah, that's right. We can't do that. That would have been interesting. Okay, so let's do, we're going to do from, we're going to take a width, so an argument which is a width, and we are going to return something of type X. So whatever it is, it's going to be of type X, something along these lines. So what is this X? How do we convert a width into an X? Width is a measurement of, let's say, length, and X is, if you want to think about a unit, it's index, and this is length from a array perspective, I guess. So in order to go from one to the other, what we do here is we say, essentially we say X and we say arg width minus 1, basically, roughly. And what we're saying is that, so if you think about something like positionally on the screen that has a width of like 5, so it's taking up 1, 2, 3, 4, 5. The index, because it starts at 0, the X is going to be 0, 1, 2, 3, 4. So for width of 5, the maximum, the corresponding index is going to be 5 minus 1, which is 4. So that's what we're writing here. But obviously it's all red. So, and also we got to keep in mind that if this is, it can't go negative because of the units that we picked, and also because in our semantically it doesn't make any sense for us. So what we're going to do is we're going to replace it with so actually let's write this out. So we can say, so we're going to take the width, we're going to do something called a saturating sub, and that's the equivalent of like this, basically. Essentially is what we're doing here, and we can say like that, but obviously there we go. So what we're saying is that in order to get, or if I write it even more succinctly, it would be something along these lines. So I'm just basically taking the width minus 1, and that's my X. So if I were to sort of keep going for height, converting from height to Y, same thing. Now going the other way, we add, we don't need saturating add, because I mean we can just say +1, but okay, I don't know why I did this. And we can do something very similar. So yeah. So essentially now we've done the conversion from width to height, width to X, height to Y, X to width, and Y to height. So both ways. So if we were to write the code, what we can do is we can say configuration tests. We can say mod test conversions, and so here we can say in a test we can say fn, we can say width, test X to width. Yeah, actually no, let's do width, width to X. So we're going to start with a width, we're going to turn it into an x, and I'm going to say x value, oops, width value, oops, why is there, okay, there we go. So, and you know, I don't like this syntax, I'm going to go with that. So I'm going to take a width, oh, there is no width type 32, look at that. So let's go fix it. So we can do impl from I32 for width, and that should sort that. Yep. Okay, so now we have a conversion from I32 to width. So so we have width, then we have, and again, I don't like the syntax, so I am just going to do this. I am just going to say x, and this is your preference, like, you know, whatever makes sense. And notice that this works. So because we defined x as it takes a thing and it turns it into x. That's why this works. So if you don't like the syntax, you could just do like this. It's equivalent. It's the same thing. So, but yeah, actually, let's keep it this way. But notice that, I mean, just note that you could do it the other way as well. So now when I do x value 0, let's not do this. Let's just say that I want to check the x value, and it should be x of 9. Or I can do x of 9. Oops, what's the problem now? I32 again. Okay, let's go fix this. Seem to have forgotten the... So implement from I32 for x, and that should be pretty straightforward. Okay, there we go. Okay, so here I'm saying that, all right, convert the width into an x value, and I can do it by writing it this way, or I can also do it by writing it that way. I can do it this way, or I can do it that way. So whatever reads best for you, you can, and actually I don't need this if I do that way. So it's up to you. I can also do it this way. So whatever looks best to your eyes, I mean, you can, that's the best approach. So this is converting width to x, where I start with a width of 10, I convert it to an x value, and oops, and so we can do, and that gives me an x value of 9. It did the conversion for me, the -1, which is really, really cool. So here we can see the tests pass. So now I'm going to do something very similar, going the other way. Actually, no, let's just continue this fn test. Let's do height. I think that's how we wrote it. Yeah, height to y. And here we're going to import that. We're going to do y and y. There we go. Oh, and this is going to say the same thing, I32. So it seems like I have forgotten to implement from I32, but that's easy enough to fix. And same thing here. From I32 for y. Okay, cool. Okay, so test still pass, yay. And then, so now I can do going the other way. So I did width to x, height to y. I can do test x to width, and just basically flipping it around. Tests pass. Y to height, flipping that around, and tests pass. Pretty cool. Yeah, so actually, let's see. So if you want, with bacon, you can, to do this, you say bacon next test dash w, and then if you want to run it again, and it just picks up, like when you change stuff, it'll run the test. So like if you put, like, you know, something wrong, it'll say no, that's not right. It's really nice. But if you want to run it explicitly, just type in. It's a really nice TUI application. I didn't make it, but the Rebel TUI engine, it's meant to make it facilitate other people building TUI applications, which are like reactive applications, responsive applications, or SolidJS or Elm. Okay, so all right, so that, I think that covers the conversions. So now I want to introduce one more thing, and there's only like 2 items left in this video. So in order to like go from like length to index, index to length, like I do this all the time in the Rebel TUI crate, where I need to see whether an index falls within a particular like bounds of its length. So if X is in bounds of the width or Y is in bounds of the height. So one way to do this is we can make a trait. We can call it check in bounds, right? And so we can say, okay, there's going to be 2 types. One is going to be the index type. The other one is going to be the length type. So this trait is going to work on two types. So like index could be the X, length would be the width. And then so here we can say something like where, actually let's do this. So let's make a function. So we're going to say function check whether it's in bounds or not, something called self. And we're going to take length, which goes impl into length, which is generic. For now, it's going to be Boolean. But see, this index is not being used anywhere, so I want to say where self can be turned into an index. So essentially what I'm saying is that I have a trait. It works with an index type and a length type, and I can check to see whether the index type is within the length, it falls within the range of the length. And Boolean, I have stopped using Boolean. I now use enums whenever. So I'm going to make an enum called check bounds, say check in bounds result, and it's either going to be in bounds or out of bounds. And I think proactively, let's put a, because in tests we'll need this. Okay, so what we're going to do is that, so the self thing is going to be the index type, and this is going to be the length type. So this is the generics. So, but that's kind of like how we're going to sort of think about this trait. Okay, it doesn't do anything yet, and also I don't want to return Boolean. I want to return check in bounds result. Okay, so in order, actually let's allow dead code. Get rid of the warnings. All right, so okay, so we have a trait and we have an enum. So, but we haven't done anything with it. So let's implement this. So we're going to say implement check in bounds, and we're gonna use X as the index and width, and the self is going to be X. So whatever's here is self. So it goes something like. So we say, let's say, actually, let's do this. So let's say let, so we have length, no, let index equals self.into, and actually we don't need self.into because it's already X. So we can just say let other equals arg length into, and we can say, here we can say this is other, let's see, dot 0. Yeah, that should work. So we're saying that if, actually let me write this a little bit better. So we can say index equals, self dot 0. And here we can say if index is other. I don't think that's that readable. So let's just roll it back. Let's just say self.0. So I'm just saying that, actually, let's do this. Actually, that's fine. Let's just leave it. So actually we can do like this, whatever's easier to read, or we can do like this. Actually, I think this is a bit more readable. They're both X, and I think this is complaining because Y, partial order. Okay, so let's go implement, where's X? Partial order for X. I am control clicking, but nothing is happening. Hello, there we go. Partial order, and I think we need to do that for Y as well. What the heck, all of them. And this one. Okay. Wow. All right. So, what's the problem? Expected X found U16. But, wait, what? Oh, I see. Boy, that's not that readable. Okay. Hopefully this makes any sense. Like, essentially we're taking X and we're extracting the U16 out of it, or whatever the underlying number is, and the other is the length. So this is the self index. Hopefully this is more readable. So if one is less than, then it's in bounds. If it's not, it's out of bounds. So similarly, we can do for height, same thing. And then let's do a test to see if this actually works. So we can say, we're going to make a test. We're going to call it mod test check in bounds. This syntax and this logic is getting a bit gnarly, but it's like, these are some of the benefits. I know it's going pretty fast from the very first example to this, but like, these are some of the benefits of leveraging the compiler to check for correctness in the code without us having to write a lot of tests or having to think too hard about, you know, whether like a usize can be used here or not, and do a lot of runtime checks and tests and so on. This way, the price that we're paying is at the early stage, letting the compiler catch it. Okay, so let's see. So we have an X value, we have a width, and so we're checking to see whether, given this X value, actually, I don't like the syntax. I don't know why Copilot always uses this. Okay, all right. So X value is X of 10, and the width is 20. So I'm checking to see whether the X falls within the bounds of this value. And the answer is yes, it does. As you can see, our tests pass. So what X would fall out of the bounds of this value? Well, let's see. We have, if it's 20, we know that 20 is not going to fly because 20 is past the width, because it's the zero index thing. So here we can say assert equals, and as you can see, the test pass. How cool is that? So at 20, it goes over. Up until 10, you know, 10, 19, whatever, 0, it's all fine. But at 20, it goes, okay, you're not out of bounds, which is correct. And then similarly with, actually this is not correct. Now we're going to do, let's do this. We're going to do a similar thing for, let's see, check and bounds, and nope, Y and height. Yeah. So here we have Y, we have height of 20. We know that Y, when you check, is in the bounds of 20, it's in bounds, yeah. But then when you make it 20, it's going to be out of bounds. And that's right. So there you go. That's off by 1. I mean, this whole file is off by 1, dealing with off by 1 errors and how to eliminate them. And I mean, for me, it makes sense to do stuff like this because it's just too much. It's a lot less thinking once I've done it this way. That, for example, the TUI code has a full-blown markdown editor and parser and stuff like that. And for that use case, this makes a lot of sense because I don't have to think a lot about this kind of stuff. I can just rely on the compiler and the type system to ensure correctness. So there you go. This in all its glory. Like, it started off pretty verbose and simple, but not simple enough. And then we added new types, and then added the add operator, and then we started doing these conversions so that we can handle off by ones, and then we introduced a trait to check whether one type is within the bounds of another, and then that's where we are now. Finally, I want to show one more example, and then we'll wrap up this video. The final example I want to show really is, compared to the other ones, is a bit made up, but it's important nonetheless. It's another. It's not related to newtype, and it's not related to into Impl, but it's somewhat related in the sense that it's an interesting way of using. When we introduce a new type, we can implement debug for it. We can also implement drop for it. You can't implement drop for usize, but you can implement drop for point, or X or Y or width or height, which is exactly what we're going to do. And the idea here is that you use something, you drop it, and you want to do some kind of implicit cleanup. But that's one use case. But here I just want to demonstrate, like, it's not just debug that we can implement for this new type. It can be drop, which is actually, there's a lot of code in the TUI code base where I have an editor, which is a full-blown markdown editor with, like, it's in the terminal. It has a markdown parser, and you can mutate it from a variety of different actions. So you can delete stuff, add stuff, and once mutations occur, a lot of things have to be validated for grapheme cluster reasons, which I'm going to do another video about grapheme clusters in UTF-8. Like, you could move your caret to the right, but if you're in the middle of what they call a jumbo grapheme cluster, which takes up, like, 2 or 3 display widths, then the caret position is actually wrong, and there's a bunch of calculations that have to be done to reposition the caret correctly, and so on. So in those circumstances, implementing drop, like, I have this mutator. I basically ask the editor, hey, I would like to mutate the buffer, and it gives me a drop handle. As soon as the drop handle gets dropped, it actually runs some validation code against the data that I have in the editor buffer. It validates cursor position and all kinds of stuff. Really powerful pattern. I wanted to show it in this video for that reason. Let's do this. We're going to make a different new type. This time we're going to call it X drop. This one's don't be concerned by the lifetime. This is just for illustrative purposes. What I want is to wrap an X, but I also want to provide a mutable reference to a basically essentially a list of X, so that we can see, like, how many, if we create a bunch of these X drops and then we drop them, we want to be able to see how many we dropped or which ones we dropped. So basically this is just the new thing. This is what we're used to seeing, but I added this new one. So now in order to construct an X drop, I got to pass in this mutable reference to a vec from somewhere else. So this will all make sense when I show you the code. So so if you do implement drop for X drop, and what we're doing here is that, let's go ahead and print line. We're going to drop, let's see, X, and we're going to push that into this given dropped list, whatever that is, and we're going to print out the state of the drop list. No, this is not right. This is dropped list. There we go. So we're dropping the whatever this value is. We're adding it to the drop list, then we're dumping the drop list to the screen. So actually, let's not even do this. Okay, so we're just saying that, okay, we're dropping X, adding to drop list. Okay, cool. So that's literally it. So now let's write a bunch of tests to see this in action. So we can say mod tests, super, and so let's do this. So we can say test drop. So let's make a dropped list, and we're gonna do it as a mutable vector. So it's gonna be a mutable vec of X, which type inference hasn't kicked in yet because we haven't written the test, but it will in just a moment. So here we say we're going to make an X value. We're going to say it's X of actually X of 10, let's say, and then we're going to make an X drop. So basically we're going to get a drop handle. So this is going to be our drop handle. So, and we can actually inline this. Let's just inline it. So what we're doing here is that we're making an X drop. When the X drop gets created, the thing that it gives back, we can drop it. So that's what actually, sorry, we need this outside. So, so basically I'm creating, this is such a contrived example. So essentially we're, why is this complaining? Okay, so here we have, as you can see, the little hint says drop handle. So when this drop handle gets dropped, X value will go out of scope. X drop will also go out of scope, and then what'll happen is that the dropped list will be populated with whatever X value was. So let's see print line. This is, oops, print line. Here we're saying that, okay, we created X drop. And then here we can see something along the lines of that. So let's run this. So it goes X drop. We created, actually, why is it being so verbose? It's weird. Let's just do this. I don't know why it's saying. Because we have our own custom debug implementation of X, so we don't need all this extra stuff that Copilot added. Okay, so X drop says, okay, you created an X of value 10. Then dropping, where did that, oh no. This is everywhere. Okay, then we say, okay, dropping that X10 and adding it to the drop list, that's great. And then it dropped X10. That's when we exited that block. So this is so created. So we should see created, dropping, and dropped. So let's see if we saw that. We see created, dropping, and dropped. And this dropped comes from the basically enumerating that list. So here we have when you create an X drop, it takes ownership of this X value. So, you know, let's just do this. I don't know why we need this. We can just inline this. There's absolutely no reason to do it this way. There we go. And we just created and instead of saying drop handle, let's just call it X drop 1. and actually just call it X drop, or just X value. Yeah, and here we say X value. Okay. Dot X. So here we have, let's run it again. So we created X of 10. We dropped X of 10 and added it this dropped listing. And then at the very end, we're seeing that, okay, we dropped X10. So that's what this means. Similarly, we can add another X value, 20 this time. And we can say, okay, we created this thing. And then actually I'm going to move this down here, and I'm going to put some assertions there. So yeah, there should be 2 items in the list, and it should be, let's say it should be 10 and 20. That's correct. And let's run this. There you go. So created next drop, it dropped it, added the drop list, created next 20, second one, dropped it. Every time it drops it, it keeps adding it to this list, and so at the very end we can see it dumped. So here we can say dropped list. So there we go. And I don't know why it prefixed everything with X drop. That's weird. But yeah, so dropped list contains dropped list contains 10 and 20 because these were added and then dropped. Completely made up nonsense example, but just to kind of give you a sense that when you have the ability to create your own concrete type, you can not just implement debug for it, you can also implement drop for it, which can open up a whole world of interesting possibilities for cleaning up resources. Once you're done, you can make a connection pool where you return the item that you took out of the pool when it's dropped, or who knows. There's many different examples. There's a whole bunch of these in the tool we create, but newtype unlocks this possibility as well. And you can always go to the I should have had this open. You can always go to the Rebel Open Core repo and check out the code base and see where it's used. Most of it, there's a whole core thing where this is littered with newtype. I mean, in fact, there's a changelog where you can see oh, that's not right. That's weird. That is very strange, whatever this is. I need to fix this. Okay. What the heck? What are you doing, Firefox? So here, newtype, you'll see many references to newtype. And you can follow that up and then check out the code. And then, yeah, that pretty much ends it for the video. If you like this style of video, please do subscribe, give a thumbs up. I actually don't have any comments enabled on videos because a lot of times they can be quite not so pleasant, and I would it's easy for me to turn it off, so they're all turned off. You can if you need to give any feedback, you can always join our Discord. Oops, I don't think this link shows up. I realized that because my face is on top of it, so there you go. So you can join our Discord. We have a newsletter if you want to sign up for that. I don't really send out that many updates to that anyway. And then you can always create a GitHub issue or reach out to me via email. So with that, thank you for watching. I'll be doing a lot more videos based on this epic rewrite I did for 3 months. And this is the first of them. So thanks again for watching, and have a great day.